Hi folks, today we're going to discuss value inherence, abductive reasoning, and building machine learning models that reflect ethical decision making. This is a presentation I gave at Gonzaga University in April of 2025. The views expressed herein are my own. Let's begin. In terms of topics we're going to explore, we're going to look at the differences between codes of conduct and codes of ethics, codes of conduct, ethics, and concepts of value adherence and value adjacency for products. We're going to contrast value adherence and adjacency with value inherence as expressed in machine learning products. We're going to look at value inherence, bias, and a phenomenon of bias, technically or introduced. We'll look at how you can ensure that codes of ethics and values and principles are reflected in machine learning products. We'll talk a little bit about best guess reasoning and reasoning to such values and principles. And finally, we'll look at a case study in the form of the Kenyan Data Labeler and ChatGPT case study. So the behavior of organizations and their employees are governed by two things. First, there's a code of conduct, which can be defined as acceptable behavior for specific situations that are likely to arise within an organization. And then there are also a code of ethics, which are broad ethical aspirations for a company and its employees. And together, the rules of codes of conduct and the values and principles of code of ethics govern organizational behavior and that of its employees. Sometimes organizations and their employees can face a dilemma when seeking to apply a rule of a code of conduct or a value or principle of a code of ethics. Specifically, when faced with an ethical dilemma or ambiguous situation, principles articulated in a code of ethics can help guide the decision maker. The following example shows how this dilemma can arise and how employees and organizations may reason out of such a dilemma. Imagine you have the following set of facts. An organization is negotiating with several other organizations to set prices for a market, thus engaging in illegal price fixing conduct. A code of conduct may say that employees must not disclose confidential company information to outside parties. By contrast, a code of ethics may say that employees and companies and organizations have a commitment to transparency and honesty in all business dealings. The conflict between those two creates a dilemma given the set of facts. So how might one reason out of this dilemma? The company person and their rationale may state that one should just follow the rules, for maybe one doesn't have the complete picture of all the facts, doesn't know the law, even if this activity may suborn illegal conduct. Another person, who we'll call the person with the higher purpose and their rationale, may reason that it seems illegal, thus it may hurt consumers. It's not honest, and thus I should disclose irrespective of the rules. So what's the outcome here? The company person, citing the code of conduct, may decide not to disclose outside the company, whereas the person with the higher purpose may disclose the existence of the negotiations to parties outside the company, citing basically the code of ethics and associated values and principles. So how do codes of conduct and codes of ethics relate to the products that an organization sells? Well, the customer may always be right, a rule, but this does not necessarily impact the quality of the hamburger they have purchased. Meaning that historically, rules and values and principles are not directly incorporated into the products sold by an organization. Rules and values and principles in products, at best, are value adherent, meaning that the product is sold reflects a code of conduct or ethics, but it itself does not contain the rules or values or principles of a code. At worst, these rules and values and principles are value adjacent, meaning that the product is sold and the rules, values, and principles of a code do not overlap. And in this case, you can think of Enron as an example of value adjacency. Different than the historical concepts of value adherence and value adjacency, with machine learning products, you have what is known as value inherence, where an organization or its employees' values or principles are directly incorporated into its products. So codes of conduct and their rules, or codes of ethics and the values and principles, are actually placed into the machine learning products. So some topics to consider. First, why is there value inherence in machine learning products? And second, how do we ensure that an organization's values or principles are reflected in its machine learning products? In the next few slides, we'll give some examples of how we might go about answering these two topics and associated issues. So we're going to explore value inherence through looking at bias as a technical matter. Bias can be understood as a difference between an estimator's expected value and the true value of the parameters being estimated. And further, any discussion of bias depends on an unknown true function. Further, bias can be addressed via concepts of data preparation and data normalization. And in the next few slides, we're going to look at these concepts and examples of them. This first example is a data preparation example, where we're going to label data to allow for the approximation of a true value. So imagine that we have an image data set of possible basketball shot adjustments, where images of bad basketball shots are labeled 0 and images of good basketball shots are labeled 1. Now imagine that the image of a St. Mary's basketball player shooting the ball is labeled 0. So St. Mary's is the arch basketball rival of Gonzaga University. All right, and so we're going to use all of these labeled images then to basically infer the ideal basketball shot. And we'll show how we'll do this in the next few slides. So the approach we're going to take to make this inference of an ideal basketball shot is we're going to use simple math functions to represent simple adjustments, such as changes to grip, stance, balance, etc., as depicted in images, to build a more complex function to approximate a true value in the form of an ideal basketball shot. And this is generally known as the concept of function approximation. So we'll pass in, during the training of this ML product, a different image of the St. Mary's basketball player shooting the ball. And in doing so, we'll build a more complex function that results in an expected value. And so is this image of a St. Mary's basketball player shooting a basketball an example of an ideal shot? It's kind of 50-50, and hence there's an error between the expected value and the true value. And what we'll try to do is, by iteratively passing in more labeled images, we'll basically try to reduce this error, and in doing so, reduce bias. So now we'll go to test this machine learning product after iteratively training it. And we'll do so by passing in a previously unseen image here of a Gonzaga basketball player shooting the ball. So when we pass it in, we see that this image approximates an ideal basketball shot. And so the takeaway here is that we've created a complex function by approximating a true value to represent a true unbiased value from a simple function, each representing a simple adjustment to a basketball shot. The second example here is that of data normalization. Here we adjust the vector representation between images to express similarity between data or an analogy between data sets, and then use this adjusted training data to approximate a true function. So here, for example, we have basically an image data set at differences between images of shots. So we have the ideal basketball shot, and the difference between the ideal basketball shot and a Gonzaga player shooting the ball is a vector distance of 0.5. Similarly, we have an ideal basketball shot and an image of a St. Mary's basketball player shooting the ball, and the vector difference is, again, 0.5. This can be expressed as the following. The ideal basketball shot is to the Gonzaga player's shot, as the ideal basketball shot is to the St. Mary's basketball player shooting. Now imagine I change the vector representation from 0.5 to 0.2 because I like Gonzaga basketball. So the distance between the ideal basketball shot and the Gonzaga player shooting the ball, and the image thereof, is now 0.2. Whereas the distance between the ideal basketball shot and the St. Mary's basketball player shooting the ball is still 0.5. This results in the following, that the ideal basketball shot is to the Gonzaga player shooting the shot, but this is not analogous to the ideal basketball shot and the St. Mary's basketball player shooting the ball. So the third example of data normalization, is where you might penalize an algorithm for using certain types of data so as to prevent certain outcomes in the form of large policy updates, such that the true value is approximated. So let me explain what I mean by this. So imagine that you pass in a previously unseen image here of a St. Mary's basketball player shooting the ball, and that you have certain areas of the data distribution were clipped. And these clipped areas may include images of St. Mary's basketball players shooting the ball. So as you process basically this image, it results in the approximation of an ideal basketball shot, but the images of the St. Mary's basketball players shooting the ball are part of a clipped image that the algorithm never considers. So the takeaway here is that you've constrained complex functions to the extent that it ventures into a clipped interval so as to more efficiently approximate the ideal basketball shot. Again, note that the St. Mary's basketball player is in the clipped area, thus isn't considered. So why is there value adherence? Well, during the training or use of machine learning products, certain values, labels, vectors, etc., are assigned or excluded while approximating the true value. And sometimes this value assignment or exclusion itself introduces new bias, which we'll call introduced bias. So that's a lot. Let me kind of summarize it for you. Basically, Ted's dislike, read bias against St. Mary's basketball, seeps into the training of the machine learning product and creates new product-based bias. That is, introduced bias occurs where a value assignment or exclusion does not reflect the facts or desired societal value. Value assignment is performed by engineers as a part of the data preparation or data normalization process. And this is why ethics training related to values and principles is critical for engineers and scientists. And by the way, I'm really not biased against St. Mary's basketball for the most part. While machine learning product that is biased against St. Mary's basketball may be a funny example, let me talk about some not so funny examples. The first is the Amazon HR classifier example. Here, Amazon sought to build a candidate classifier to identify the best programming candidates, and they did so using data of successful candidates. The problem is that as a historical matter, the distribution of men versus women programmers is 80-20, meaning that 80% of the programmers in the US are men, 20% are women. The result of this is that the resumes of women who were passing this classifier resulted in a determination not to hire. Another example is the coded bias example. Here, certain parties sought to create a facial recognition classifier that could then be used to determine whether physical access should be granted to a facility. Historically, the data distribution of African American versus non-African American developers is 7% African American, the rest non-African American. So here, they used a number of images to train this classifier where the number of African American images and faces was underrepresented, such that when images of people with dark skin tones were passed in this classifier, the determination was made not to grant access. So how does one ensure that an organization's values are reflected in its machine learning products? So one possible solution is to update the code of conduct and create some new rules. The problem is that rules have problems with scaling. That is, rules don't scale well given the complexities of the world, and this is a problem with the rule itself. Let me explain what I mean by that. Imagine you have the rule, birds fly. Well, this is true except for penguins, ostriches, birds with broken wings, and so on. Or maybe you have a rule in the form of never tell a lie. Well, this may be true except for when a murderer is at your door asking about your friend who lives with you, or maybe when you're speaking to your boss, friends, spouse, kids, and so on. The problem is that rules are generally brittle given the complexities of the world. Another problem with rules is ambiguity of application. Namely, it's not clear what rule applies given the ambiguities of the world. And this is really the issue of decision boundaries. Namely that where there's only two options in explaining a particular world, everything separates out very, very nice and cleanly into basically 0, say St. Mary's basketball, or 1, Gonzaga basketball. But things break down when you introduce additional variables. So imagine you have your world where everything breaks down neatly into either St. Mary's or Gonzaga basketball. And you introduce a new player who we'll call Goofy, who is sometimes a Gonzaga player and sometimes a St. Mary's player. This then raises what's called the curse of dimensionality, which is, in the abstract sense, a number of different features. As the number of different features or dimensions grows, the amount of data we need to generalize accuracy grows exponentially. So the solution would be typically that you would need a lot more data to find a decision boundary as between Goofy and Gonzaga or St. Mary's basketball players. But sometimes engineers or scientists default to introduced bias to fill gaps in understanding the applicability of a rule. Another possible solution to introduce bias is what we'll call best guess reasoning. We can describe this as ascertaining the facts of a situation and reasoning to a value or principle of a code of ethics. And this is generally just abductive reasoning. So let me give you an example by contrasting it with deductive reasoning. So in deductive reasoning, maybe you have the following. You state that if Gonzaga wins, then Mark Few, who's the Gonzaga coach, will be happy. And you know that Gonzaga wins, so Mark Few will be happy. Best guess reasoning, for example, maybe you see, for example, a puddle of water, and then you reason to that by saying that it rained recently, which most likely caused the puddle of water and is the most likely explanation for the puddle of water. So let's consider best guess reasoning as addressing introduced bias. First, remember that the complexities of the world are such that rules aren't enough. And this requires that one train a number of employees, such as data labelers, on a number of different scenarios that require the application of a code of ethics using best guess reasoning to render a labeling decision. So what's a case study to apply this approach? A few years ago, there was an article titled "OpenAI Used Kenyan Workers on Less Than $2 per Hour to Make ChatGPT Less Toxic." Basically, what happened here is that OpenAI employed data labelers in Kenya to label certain types of content as toxic or non-toxic, and then use that to build a filter for ChatGPT. We're going to discuss this in the next few slides. So what's an example of where best guess reasoning may have helped? Well, it's this Kenyan data labeler and ChatGPT example. ChatGPT sought to build a text filter to remove toxic text because, of course, you can never create enough rules for this task for how many different swear words are there in the world. Okay, so to do this, they employed data labelers to take internet text and label it either toxic or non-toxic to create a training set. Problems arose, or dilemmas that is, when you have ambiguity regarding the consensuality or not of particular relationships between people, because it's uncertain in certain cases whether relationships as depicted in text are consensual or not. So a possible solution to the dilemmas or ambiguity of the labeling activity engaged in by the Kenyan data labelers would be to promulgate values or principles such as respect for autonomy, prohibition against violence as part of a code of ethics, and then have these employees attempt to reason to or make best guess as to the applicability of these values and principles, such that the employee determines whether the text reflected a respect for autonomy or support for prohibition against violence, and effectively allowing them to reason out of any dilemmas. And they could repeatedly do this. What actually happened, however, was that OpenAI provided no guidance on how to resolve dilemmas regarding the consensuality of, say, text and the relationships depicted therein. As the article reported, should the passage be labeled as sexual violence, she asked or not, OpenAI's reply, if it ever came, was not logged in the document, and the company declined to comment. Summing it up. Codes of conduct describing acceptable organizational behavior for a given situation, while codes of ethics describe aspirational organizational values and principles to be applied in the case of ethical dilemmas or ambiguous situations. Rules and values and principles are not directly incorporated historically into products that an organization sells, and at best manifest value inherence or worse, value adjacency. Value inherence is unique to machine learning products, as the values principles are incorporated directly into the product as part of reducing bias during the training and testing process for the machine learning product. Introduced bias can arise during the training process, where the party labeling the data for training adds their own biases directly into the data as a manifestation of value inherence. Rules alone are insufficient for addressing introduced bias. This due to the complexities of the world and scaling rules and the ambiguities of applying such rules. Best guess reasoning, leveraging values and principles for resolving ethical dilemmas and ambiguity in labeling data for training machine learning products, can be applied. I hope you've enjoyed this presentation.